Hello everyone, in this video we're going to build this custom particle system in the geometry nodes using simulation hack. In this video I'll also show you how you can use this same node setup in the Blender 3.5 which is released with the simulation nodes, but it is in the alpha stage. But this node setup works completely fine, particle system. And I'll also show you how you can transfer your hack algorithms directly to the simulation nodes in Blender 3.5. So let's get started. So first we're going to build this particle system, and it has three main parts: the simulation input node, output node, and the particle checks. So this node basically contain or define the settings of the particle system, like all those attributes that are needed for the particle, and then we're going to check whether the particle is dead or not on each frame. And then this node is update the velocity and position of the particles based on these forces. I'll also show you a general force group node. On top of that you can build your any custom force. So let's get started. So this is the basic setup for the simulation hack. So here is our buffer object which takes the geometry from the simulation setup, sim setup, and this is the sim setup. So if you haven't seen my previous video about the simulation hack and how does the simulation works, then I highly recommend you please check that video, so it help you to understand the simulation concept. So we're going to build the particle system first, and then the forces, and then we will transfer this particle system to the simulation nodes in Blender 3.5. So let's first build the particle input node. So let's move this side, these nodes, and also this one. We don't need this end frame switch node. So let me add 2 frames just to outline our setup. So this will be our particle checks, and this will be our particle forces. We're going to combine these together to make the particle output node. So first we're going to initialize the data for the particles. So let's add the distribute points on the faces node, and we have these points. And next I'm going to make a group with these two. Okay, so first will be our input is an initial buffer switch, and second is the geometry, and this is also the geometry. So first we want to output these parameters. First will be the seed, then the selection and density. Next I'm going to output this as our start frame. So this is start frame. Then also duplicate this one. This will be our end frame. So let me specify numbers for these frames. First frame, okay, and next end frame will be 50. Okay, these are not the simulation start or end frame. This is for the particle system, as we have the particle system in Blender. So I'm keeping the settings similar to the particle system that we have already in the Blender. Okay, yes, this will be particle system input. Fine. So next we're going to store the attributes. Sorry, let me disable this. So first we're going to store the born time of the particles. Okay, let me show you time axis for the particle. Yeah, here it is. So this is what we're going to do. So this is the time, or you can say scene time, before when the time is less than the born time or born frame. These attribute will be false, like is born means particle is not born, and particle is not alive, and particle is not dead. All the attribute will be false. And when the current frame or the scene time is greater than the born time, then these flags or these attributes are like born is true, alive is true, and dead is false. And this time is basically the age of the particle, and this whole time is this range of the time is the life of the particle. So when time is greater than the lifetime of the particle, then we know the particle should be dead. So that is true. Alive is false. And the born flag will never change. It only change when the particle born, because no particle should be born twice. So this is how we're going to implement these flags for the particles. These time flags or attributes are very important to run this particle system. So first we're going to store the born time. So I'm going to use random minimum, start as a minimum, then this end as maximum. So in between these frames, the born time will alive for these particles, and this is connect this to this seed. So we have the born time of the particles. Next we're going to add the born flag. Is born, particle is born or not. And for that, let's add the a scene time. So if this time is greater than the born time, greater than and equal to the born time, then this flag will be true, as I have shown in the image. Means when this time is greater than the born time, is born is true. So we have born. Next we're going to add the life and then age. Then we're going to add the alive and dead. Okay, so this will be age, so integer, and this is first we're going to store the life, what will be the total lifetime of the particle, and this will be the age. Next is alive, whether the particle is alive or not based on born time and the lifetime, and this will be the dead, is dead or not. So now for the life, I'm going to use the same this random node. Let's disconnect these. So we're going to use maximum as the life of the particle, and if we want to randomize the life of the particle, we're going to use the map range node. This way you can control the random values with one factor, like probability. Use this as minimum, this is 0. So when this parameter is greater than 0, then we will have a random life. So this is as life random, and now we have the life. And to calculate the age, so basically we have to add the subtract node. So we have to subtract the born time from this frame. So we have this age, and if scene time is less than the born time, this can be negative. So we need a maximum node to clamp that, and this age shouldn't be greater than the lifetime of the particle. So we're going to clamp this with this lifetime. So this is the age. So let me go outside this group. So we have 100 and this is 1. Now let me show you these attributes in the spreadsheet. Also make this one, so we have only 4 particles. So this is the born time between the 1 and 50th frame, and this is the lifetime. Age is 0 because no particle is born yet, and is born is false, alive, and other are also false. Now let's handle this alive flag. So for that, a particle only be alive when the time is greater than the born time and less than the lifetime. Okay, To do that, we have this one at the end node. This is greater than the burn time, and it should be less than the lifetime. So when this is, or we can use this one, and this is without clamp. So when this is less than equal to the life, means when this our calculation of age is less than or equal to the life, then particle will be alive. So connect this to this one, and next when this calculation or the age calculation is greater than the lifetime, then this will be not true, so particle is dead. Or you can use another node which is like means this calculation of age is greater than the lifetime of the particle, then particle should be dead. This is the same thing. Okay, I think we have completed the time attributes. Next we're going to add other attributes like the velocity, rotation, size, mass, etc. So let's first store the time step. So what is time step? Later in this video I explain this in detail, but right now in this you can think as it is required to calculate the velocity and position from the force. So this time step is required, and it is there in the particle system, if you have seen that. So default, let's say it is 0.1, and next we're going to add the velocity. Velocity should be vector velocity, and then we also add another one. This will be velocity from force. And next we need is for the rotation, and I think we should add the radius and mass of the particles before the velocity. Right now it is not it doesn't matter how we store them, it is just for the clearance. So this mass, radius is float, and also the mass. Let's call this as size. By default it is 1, and this is mass of the particle, and another one maybe the color of the particles, color. So we have added all the attributes, I think, and let's duplicate this. And first I'm going to output this life, after this is size, then the mass, then the color, and then we will output the velocity. This is not required, and the rotation. And here we can also use this normal as a normal velocity. Okay, this maybe you have seen in the particle system. We have the normal velocity, means velocity of the particle based on the normals of the base mesh, and then we need vector add node and use this as the velocity. So this is like our initial velocity, and this is our vector for that normal velocity here. And in the end I'm going to store the this time step. So first is size, then mass, then color, velocity, normal velocity, then we need, this is the rotation. Okay, rotation. So let's set the default value for these attributes. See, it's fine, dense is fine, start can't be negative. I think start can't be negative. Let's keep this negative, and it's okay. Life can't be negative. This random life is 0 to 1. Size can't be negative, but size can be 0. Okay. And by default it's 1, and mass can't be negative and 0. This Okay, this is the lower limit. You can change according to your need. And velocity is okay, normal is fine. Rotation, this is the time step, and time step can't be negative and should not be 0, otherwise the velocity and position will blow up from the forces. When we add those, then it will be clear for you. So I think it is done with this input node. So we have all these settings, and if you want to further add these attributes, you can also add those here, or you can add these attributes after this node. Okay, so now let's build on this particle checks. So let's make a group with this. Okay, so we have this particle check. So let's name this as particle checks. These checks should be done on each iteration, or you can say on each frame. So we have to check whether the particle is alive or is about to born and is dead or not, and then we have to also change the age of the particle. So let's first reset or change the attribute of this born flag. Change this to boolean, and this is, let me go to the first frame, then second, this is born, just to refresh the this buffer loop. So is born. Now let's add the scene time. So when this time is greater than equal to the born time. So let me add this from the named attribute born time. So born time, so that will be an integer, so greater than equal to. So when this time is greater than the born time or equal to the born time, the particle will born. So add this to this, and let's see those attributes. Go to the first frame, and the born time of the particle is 2, see, and right now the current frame is 1, and the is born flag is false. Now if I go to the second frame, see, the particle born flag is true, means particle is born. And next we're going to change the age of the particles. Age, let me recapitulate the previous calculations. So here we set the age, so we subtract this frame from the born time, then use maximum, and then use the clamp node, then use this as our age. So we're going to do the same calculation in the checks again. Okay, so add this and the subtract, and subtract this born time from the frame, and this can be a negative, so add the maximum. So let me show you. If I use this as age, let's use before the maximum. See, the age can be negative, then it is positive. And if we go to the fourth frame, the lifetime of this first particle is 3, means it only live for 3 frames, and then a should be 3 after that frame. That number of frame is second, third. See, it is increasing, so that's why we need to add the clamp node. So we're going to clamp this with the lifetime of the particles, as we did in the input node. Now let's go to the first frame, plug this as age. See, it is clamped. So we have fixed the age. Now next we're going to update the alive flag of the particles. So particle will be alive when it is born, and the time scale, this time scale is less than equal to the lifetime. This as this. Now let's go to the first frame. See, particle born, flag is alive, and let me see what is happening. Okay, when this is particle is alive when this is less than the lifetime. Oh, sorry, I haven't entered the born time to this, so we have to add that this. So total life on the total time we need is the born time plus the lifetime. That will decide the time limit for the particles. Let me go to this layout. So here we can see, so this is the life and this is the born time. Together will give this limit. Okay, so that's why we have to add that. Now it should be correct. So particle is alive. See, it is alive for 5 frames, and 2 plus 3 5. At the 60th frame, it is alive flag become false, and particle become dead. So let's update on this. This is dead flag. This will be true when the particle become dead. So there is 2 ways to do that. I'm going to use this age as comparison. So this means this calculation of age without the claim when this is greater than the life of the particle, then the particle should be dead. See, alive, then dead flag become true. This is what we are expecting from that diagram. You can also use these comparison for the live as well. Means we can also do this like when this is not, means when the particle is not dead, this particle is born and it's not dead, then this live flag is true and it will work, will give the same as, yeah. So we can use that instead of this. This is much simpler and easy to understand. This is for the dead, and this is when the particle is not dead and is born, is alive. When it's dead, this will become false, and the particle alive flag also become false. So we set these, and next we going to reset the velocity of the velocity from the force attribute, because at each frame this velocity will be calculated from the force and then added to the velocity of the particles in the particle output node. So we have reset this velocity in this checks. It is completed. So we have completed the checks node, and next we're going to do the particle output node, and then we will build the forces. So let's group this, and here move this upside, and this is will be our initial geometry, you can say. This lower input is the buffer geometry, or simply the geometry. So here we're going to update the position of the particles and the velocity of the particles. Also rename this switch as initial buffer switch. Let me check the names. Initial buffer, it's fine. Okay. Rename this as particle system output. So we let's build that. So let's also add the stored attribute node, and we're going to update the velocity of the particles. This should be a vector, and next add the named attribute. First we need the live flag, because we only going to update the position and velocity of the particles that are alive, not the particles which are not born yet or the particle which are already dead. So then duplicate this. We need the velocity, existing velocity of the particle, and velocity from the force. So first we're going to multiply this velocity with the flag. So this ensure that the particle which are dead or not born, they have zero velocity from the force. Next, add this to the existing velocity of the particle and use this as input for the velocity. Next, we're going to multiply this with the time step. On time step, I'll explain what is this step, and then plug this as our offset and connect this flag to the selection. Means we are updating the position of the particles that are alive. So we have completed the output node. Now let's see this. Let's add initial velocity to the x direction. See, it's working. Right now it seems all the particles is moving, or they are visible, so we can hide them, those particles which are not born yet. So you can't delete these points. Yes. Okay, we have to just use a trick. Means either we can make their size 0, or you can use the live flag when we render these particle in a different object. Only instance the object on those points which are alive. Okay, we can't delete these points, otherwise we don't have any sequence to handle the particles. So let's add the switch node and change this to a float, and when the particles are alive, they're going to have a say 0.1 radius, otherwise 0. See, now as they become dead, they disappear, or when they are not born. Okay, now let's change these settings. Maybe under density, first frame, and lifetime around 250, and randomness 0. So working, and if I change this to say 100, yeah, it's working fine. Now we're going to build the force. So first I'll explain how we're going to calculate the velocity and position from the force, and then we will build the force group node. So this is Newton's formula for the force. So force is equal to mass into acceleration. So to get the acceleration from the force, we have to divide the force by the mass of the particles or the object. So now we have the acceleration from the force, and acceleration is equal to the slope of the velocity, or you can say time derivative of the velocity. So if we multiply this a with dt, we get the velocity from the acceleration, and similarly velocity is slope of position or the time derivative of the position, and from this we can get the position from the velocity, and velocity from the acceleration, and acceleration from the force. And then we have these new values for the velocity and position. Then we're going to add these values to our previous velocity and previous position. We get the new velocity and new position, and that's what we have did in this particle output node. We have the velocity from the force, we add that to the existing velocity of the particle, then we have new velocity, and similarly we multiply this velocity with the time step, we get the position, and we add that to the existing position. This offset is like adding some value to the positions of the particles. Okay, so this is how the force is this calculation works for the particles. And next we're going to build the central force or the gravitational force. So this is the formula for the gravitational force. G is the gravitational constant, then mass of the central object, mass of the particle, and distance squares. Because we if you remember the previous formula, force acceleration is force by mass, so E is just minus gm by r square. So if we treat this as 1, then we have a is equal to 1 by r square. You can put a real value for these constant if you want. So let's first build the central force. So let's add the store attribute node, and I'm going to, let me unparent this, put this outside. Let's plug this into this, and this should be vector because we're going to update the velocity from the force. So we have this, and next we need to make the nodes for this formula. So let's add we need a central object. Let's add the empty here like there, and now let's bring this empty, make this relative. So we have to subtract this position from the position of the particle to get the radial displacement, and then we're going to calculate the length or the distance, and then we're going to multiply this distance with itself to make it is power 2, or you can also use the power factor. Remember this, we have this. So we make the square of the distance like in this formula, and now we have to divide the 1 by this distance to get this acceleration. So this is like the magnitude of the force, and because some of the particles may get very close to this central object, and then this force may blow up. So we have to clamp this, and I'm going to clamp this between 0 to 1. Now let's get the direction from this displacement vector by normalizing this, and then use the multiply node, multiply this magnitude to this direction. So we have this force. So let's make a group for this, Control G, and I'm going to add another multiply node to control the strength of this force. Multiply this and also output the object. So let's rename these. This is strength. It can be negative or positive to make this force attractive or repulsive. So they change this to a float. So this is our formula for the force. So now let's put this in a frame, force formula, and then we're going to multiply this force with the time step. Remember these equations. So to get the velocity, we have to multiply this with dt. So add the name attribute node, and it goes to the first frame, then the second to get the time step. So we have the time step because we're going to only update the velocity of the particles that are alive. So even though I have multiplied the is alive factor in the output node, but I'm going to again multiply this with that factor here, just to ensure that this force is only updating the velocity and position of the alive particles. So we have this, and next right now this force is independent of the mass of the particles, means this acceleration, because we already divide this force by the mass of the particle. So we don't need to divide this force by the mass of the particle. However, if you suppose this is any another force, and then you have to divide this factor by the mass of the particle, then use this as the multiplication factor. So let's put this in a frame. So this is like a mask, time step, and mass, and then we're going to add this velocity to the velocity from the other forces. Means if you connect these forces in a series, then we may have a velocity from other forces. So we have to add this velocity, this one, to the existing velocity from the forces, and then this will add up in the output node to the existing velocity of the particle like this, and then put this in another frame. So let's rename this as this step is essential for all the forces. So basically, if you want to build your custom force, then write the formula in this section for the force and then repeat this step. So if force is depends on mass, then use this factor, otherwise use this one like we are using in this case. And I'm going to name this as central force, and let's see this. Okay, it's positive value attractive. I'm going to swap these inputs to make that negative value is attractive. Let's make 3 strength. It is attracting the particles, maybe 5. So actually this force, the formula and the calculation for these particles are accurate. These particles should make orbit around the central object under the influence of this force, but they are making the spiral. So maybe there is a loss of velocity in this station setup, or so this force is not working fully accurately. So now let's build another one as a turbulence force and duplicate this, and let's change the name of this turbulence force. Let's make the strength to 2.5. So let's add the noise texture color. So we're going to subtract 0.5 from this color, because we want to deal with the direction of the noise field, not the magnitude of the field. Okay, so let's make this detail and roughness 0, maybe default say 3, change this to 4D, and I'm going to multiply, add this frame node, and then add the multiply node to control the speed of this noise with respect to time. So let's output this one. This is scale and this is the speed, and we can delete this. We can also add another multiply node to control the direction, in which direction this noise affect the particles. So let's add another multiply node here, duplicate this, change this to normalize. So why I'm adding this normalize? To make sure that even if I accidentally type larger value here, then this shouldn't affect the force, because this only specify the direction or the axis of the force. And we have to multiply this with this direction and then use this for our main step. Even if you want to divide this force by mass, you can divide this. Means if I divide this, then what happen, the heavier object will affected less by this turbulence force as compared to the lighter one or the lighter particles. So let's use the mass in this force. So we have this. Let me change the default. All the axes should be 1, speed is 0, and scale is okay. Then the strength in this case only positive. So let's see. Oh, sorry, I haven't added these axes. That's why it's not working. Let's also add some speed to this. So similarly, you can build all the different forces just by following these steps. So how you can render these particles in the simulation hack? So let's add another object add this geometry node and bring this sim setup to this, change this to relative and use this as the output geometry. And then we can hide our sim setup. So we have these points. So let's name this as particle render, and also name this as particle render, and we can also change this as particle system and also the name of this particle setup. So we have these. Now let's add the instance on points node, and I'm going to instance the cubes. So see, we have cube, all the particles, even the particles which are not born yet. So to handle this, we're going to use live flag. So now this is before and this is after. Let's change the scale to 0.1. Yeah, it is working. Now suppose if you want to change the size of the particle based on their age, so it is very easy to do with these named attributes. Just search for age and then also add another one which is life. So we're going to map this age between 0 to 1 factor, use this as maximum, and let's plug this to the scale. Now the particle, when they born, they're going to have 0 scale, and as their age grow, their size will also grow. See, you can also use the velocity to align these particles to the direction in which they are moving. You can combine different attributes to control the behavior of these particles. So now let's use this setup in the Blender 3.5 but with the simulation nodes, not the simulation hack. I have downloaded the latest Blender 3.5. So this has the simulation nodes. Let's first open the setup that we just made with the simulation hack. So this is the setup we just made, and this is working with the simulation hack. So now we're going to use the simulation nodes. Let me disconnect this. So this is the simulation input node, takes the input geometry from outside, and then we have the simulation output node. So here you will basically do your simulation or build the algorithm inside these two nodes, and then it output the geometry that you can render directly. Okay, so it has another inputs like run the simulations, and then delta time and elapsed times, and then you can stop the simulation, and also option to cache this simulation. And then we have other outputs like whether simulation is starter or is ended, then elapsed time and geometry. Okay, so what we're going to do is, so you can think this previous data frame or buffer object as this simulation input node. So let's disconnect this and use this as the input for the particle checks, and this will be our input geometry to the simulation input node. And for the output thing, disconnect this, and we're going to add the simulation output node here. So connect this to the geometry and this to this set point radius node. So here you can use this as initial if you want, and use this switch as the initial buffer switch. Now if I do start from the first frame, see it is working, and we are using this for the rendering, but now right now with the simulation nodes we can use this setup directly in our particle setup, so we can render these points directly from here. So let's add on the instance on points node, and then use cube mesh, and instead of this I'm going to use this directly to the selection. So let me decrease the radius of these cubes. See, it is working fine, and we can do the same, like add the age and then add the life and map the age based on the life to the maximum and to 0 to 1 parameter. Yes, then use this as for the scale. See, the same result. So in this way you can transfer your hack algorithms to these simulation nodes. Remember this in alpha stage, so it may crash in some cases, but this is really nice to see the simulation nodes in the geometry nodes, and we can do many amazing things. I was doing many experiments with this simulation hack for different algorithms. So one of them is like close packing. So if you want to see that video, please let me know in the comment section. So this is it about this tutorial, and if you like this work, then please do support me and subscribe to my channel for more updates. Until next time, happy noding. Bye.